Hey guys, unfortunately I can't be there with y'all to go through the problems, but um, here I am recording the problems. Okay, so this was this is the contest as of right now. It is possible that I might end up having changed the problems. Hopefully it wasn't too tricky. And most of these problems, I'll just go through the sources first. This is from Singapore. This is classical. This is from AMC 12A 2014. Singapore, 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 and Singapore. I have discovered that I really like the Singapore. They're all from like the first round, the Singapore MO round 1, which is Singapore's first round contest. And I quite like them. And they're also, there's no way that any of you have actually done these problems before. So it's another great reason to use them. Okay, so problem 1. If S is the sum of all the real roots of the equation x squared plus 1 over x squared equals 2022 squared plus 1 over 2022 squared, find the floor of S. And so the way you handle this is that if x is a solution, then so is negative x, because the equation has x squared terms, so it doesn't matter if you flip the sign. And this means that you can pair off each of the real roots into x and negative x, which sum to 0. And so all of them sum to 0, and the answer is 0. And yeah, the roots actually end up being like, you can actually find all 4 roots. It's not too bad, but yeah. Okay. Problem 2. Find the value of the sum S. Find the value of the sum 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4, blah, 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 up to 1 over 99 times 100. And so the idea here is to telescope. This is the most classical telescope example. So you do 1 over k times k plus 1. That's what each of the terms are effectively. And then you write this as 1 over k minus 1 over k plus 1. Because this is like k plus 1 minus k over k times k plus 1. And so then our sum S becomes 1 minus 1/2 for the 1 over 1 times 2, plus 1/2 minus 1/3 for the 1/6 term, all the way up to 1 over 99 minus 1 over 100. And then we can cancel terms like this and this cancel, this and that will cancel, yada, yada. And so we get 1 minus 1 over 100, which gives 99 over 100. Okay. Problem 3. The first 3 terms of a geometric progression are square root of 3, cubed root of 3, and 6th root of 3. What is the 4th term? So for a geometric series, we're multiplying it by the same thing each time. And that means that we're basically adding the same amount to the exponent each time. So the exponents should be an arithmetic progression. So GP and AP. So if we write the 4th term as 3 to the x, then we have it 3 to the 1/2, 3 to the 1/3, and 3 to the 1/6. 3 to the x are a geometric series. And we also have that then the exponents 1/2, 1/3, 1/6, and x are an arithmetic series. And we note that each time it's going down by a 1/6, from 1/2, 3/6, down to 1/3, 2/6, down to 1/6, and then down to 0. And 3 to the 0, plugging that back into like the actual values, 3 to the 0 is equal to 1. Okay. Problem 4. Let S sub n equal 1 over 1 times 3 plus 1 over 3 times 5 plus 1 over 5 times 7 plus dot, 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 up to 1 over 2n minus 1 times 1 over 2n plus 1. Find the value of n such that S of n takes the value of 0.48. So we do basically the same thing as in problem 2. You take 1 over k times k plus 2 is equal to 1/2 times 1 over k minus 1 over k plus 2. We have a 1/2 term because the numerator of this thing will be a k plus 2 minus k. So it'll be a 2 up there, and we have to cancel that out. And so when we write out S of n, we get 1/2 times 1 minus the third plus 1/2 times the third minus the fifth, plus all the way up to 1/2 times 1 over 2n minus 1 minus 1 over 2n plus 1. And then as before, since we're telescoping, this cancels and yada yada. So we're left with 1/2 times 1 minus 1 over 2n plus 1. And we're trying to find the value of n, so this is 0.48. And then solving, this becomes 1 minus 1 over 2n plus 1 equals 0.96. 1 over 2n plus 1 equals 0.04. So then 2n plus 1 equals 25, and n equals 12. On to problem 5. So let I be the complex number square root of -1, and n be the smallest positive integer, such that square root of 3 plus I to the n is equal to a, where a is a real number. Find the value of the floor of n minus a. So the idea here is that square root of 3 plus I is equal to 2 times cis of 30. Cis of 30 degrees specifically, because cis of 30 is square root of 3 over 2 plus 1/2 I. And the nice thing about this is that when we raise square root of 3 plus I to the nth power, we get 2 to the n times cis of 30n. And we want cis of 30n to be a real number. And this happens when it's like either a multiple of 360, so it's a positive number, or a multiple, or 180, so it's a negative number. So we choose n equals 6. So then root 3 plus I to the 6th is equal to 2 to the 6th times cis of 180. And cis of 180 is over here. So that's -1. And so this equals -64. And that means that n minus a is equal to 6 plus 64, which gives 70. Problem 6, given that f from the reals to the reals, such that f of a squared minus b squared is equal to a minus b times f of a plus f of b for all real numbers a and b, and that f of 1 equals 1 over 101, find the value of the sum from k equals 1 to 100 of f of k. So the first thing I noticed is, like, before even reading this second line of text, is that f of x equals x works. Because then it just becomes a squared minus b squared equals a minus b times a plus b, which is well-known identity. But we want f of 1 to be equal to 101, but we are fine as long we can just chuck a 101. We can just chuck a 1 over 101 in front. So f of x equals x over 101. And we're fine because this multiplies both the left side and the right side of the condition by 1 over 101. And so now this just becomes the sum from k equals 1 to 100 of k over 101, which is 1 over 101 times 100 times 100, 1 over 2. That's like the 50, it's like the famous Gauss 5050 example, and this gives you 50. Problem 7. Each cell of a 20 by 20 table is filled with a number which is either -1 or 1. For I equals 1 through 2020, let R sub I be the product of all the numbers in the ith row, and let C sub I be the product of all the numbers in the ith column. Suppose R sub I plus C sub I is equal to 0 for all I equals 1 through 2020. What is the least possible number of -1s in the table? So firstly, note that all R sub I and C sub I are either 1 or -1. Because they're a product of 1s and -1s. And then so this means that R sub I plus C sub I equals 0 means that one of R sub I is 1 and one of C sub I is -1. Oh, one of R sub I and C sub I is 1 and the other is -1. And this gives us a way to bound the minimum number of negative ones we have to have. Because for each value of I, for each of the 2020 values of I, there has to be at least one negative one in, for all I, there exists, for all I, there's a negative one in either the ith row or ith column. And so this means that but each negative one can only like contribute to 2 values of I. So that means that there are at least 2020, because there's 2020 different I values that we have to handle, and divided by 2 because each negative one can only handle 2 values of I. So there's at most 1010, there's at least 1010 I's to handle everything. And this, like, we can do this with only 1010 by doing this setup, where we put negative ones, half, like we fill up half the main diagonal with negative ones. And then for each pair, for each value of I, you get exactly 1 negative 1 inside of the whole of R sub I and C sub I. Okay. Problem 8. Assume that the sequence a sub k follows an arithmetic progression with a sub 2 plus a sub 4 plus a sub 9 equals 24. Find the maximum value of s sub 8 times s sub 10, where s sub k denotes the sum a sub 1 plus all the way up to a sub k. So firstly, we write a sub k as a plus dk, where d is going to be our common difference. And so then 24 is equal to a sub 2, a plus 2d, plus a sub 4, a sub 4d, a plus 4d, plus a sub 9, a plus 9d, which equals 3 plus 15d. And to simplify things a little bit, divided by 3, so a plus 5d is equal to 8. Don't need that from now. And so now we just, with that in mind, we should write out what s sub 8 times s sub 10 actually is. And so that ends up being s sub 8 is equal to 8a plus 36d, because it's there's 8a terms, because it's a sub 1 all the way, sum of a sub 1 plus a sub 2 all the way to a sub 8. And then we also have a sub 1 has a d term, a sub 2 has a 2d term, so it's 1 plus blah blah, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8, which equals to 36. Through the same logic, s sub 10 is equal to 10a plus 15d. We can pull out some common terms. So 4 times 2a plus 9d times 5 times 2a plus 11d. And then this is where what I did earlier comes into play. We write 2a plus 10d as 16. And then that way we can write this as 16 minus d, and this as 16 plus d. So this gives us 20 times 16 squared minus d squared. And since we're trying to maximize the value, we should take d equals 0 here. And so we get 20 times 16 squared, which is 5,120. And last but not least, problem 9. So we let a sub k equal a plus dk as before. So a sequence a sub I is called a good sequence if s sub 2n is a constant for all n greater than or equal to 1, where s sub k denotes the sum a1 plus a2 all the way up to ak. Suppose it is known that the sequence ai is a good sequence that follows an arithmetic progression. Determine a sub 20 if a sub 1 equals 1. So doing the same thing that we did here to get like this thing, we do the same thing here. So s sub 2n is equal to 2na plus 2n times 2n plus 1 over 2 times d, and s sub n is equal to na plus n times n plus 1 over 2 times d. And oh, there we go. I got the notification for the code jam round, which is why I can't be there with y'all. And so the way I went about this is I noticed that as n gets really large, this ratio becomes close to 4. And this is because as n gets really big, the important terms are this one and this one. So the limit as n gets really big, or as n goes to infinity, becomes 2n times 2n over 2 times d over n times n over 2 times d, which equals 4. And so if this is true for all n, this means that if n at n equals infinity, this value is 4. That means that at all values, it's equal to 4. And then now you can cross multiply and expand. So you get 2na plus 2n plus 1 times d. Oh wait, I'm just going to rewrite this. So we get 2na plus n times 2n plus 1 d is equal to 4na plus 2n times n plus 1 d. And so we cancel out factors of n. And so we get 2n plus 1 d is equal to 2a plus 2n plus 2d. So 0 equals 2a plus d. But we also know that a sub 1 is equal to a plus d, which is equal to 1. So this is equal to 1 plus a. So a is equal to -1 and d is equal to 2. And based on this, a sub k is equal to 2k minus 1. So a sub 2020 is equal to 4039. And that's that. That is end of review. And I'm going to go and have lunch now. All right. Bye.